Let's calculate the self-inductance of a solenoid using the stored energy method in the magnetic field. So we begin this method by setting up our solenoid. We can say it's a radius r, it's a height h, and again, for simplicity, we're going to assume that h is much, much bigger than r, so we'll use our approximations for a very long solenoid, and then we can use Ampere's law to get the B field. Now, our stored energy is equal to the integral of the energy density over the volume enclosed, and the stored energy, the energy density is 1 over 2 mu naught, and that's unfortunate that we have, let's make this magnetic energy density, distinguish it from that constant, times B squared. And we've seen that this is 1/2 L I squared, so L is 2 times the stored energy over I squared, and that's going to be our tool. And you'll notice that in order to do that, we have to calculate the B field. And in the solenoid, the B field is uniform. And so this will just be the energy density times the volume of the solenoid. And again, to calculate the magnetic field inside a solenoid, we're assuming that B is 0 outside. That's our Amperian loop. And this was a calculation that we've done a few times. We know that B times L on the one non-zero leg is equal to mu naught. Now, again, we have to indicate the number of turns per unit length, turns per length, and that the amount of current that cuts through is just the number of turns per unit length times the length of the Amperian loop times the current in each one, and that shows us that B is mu naught N I. And so our energy, this is uniform, is just equal to mu stored magnetically times the volume. So that's 1 over 2 mu naught times B squared. So there's a mu naught N I squared. That's our B squared. And the volume is just pi r squared times h. And, well, let's just clean this up. And we'll write it as mu naught little n squared over 2 pi r squared h times I squared. And now we're looking for the self-induction, which is 2 mu U, energy stored magnetic, over I squared. And we just have now made that calculation. So we get mu naught little n squared times pi r squared h. The 2's and the i's squared cancel. And now we can say that if there's n total turns, that the number n, little n, is total n over h. And so we can conclude that this is mu naught n squared pi r squared. There'll be an h squared downstairs over h. And that agrees with what we had before for calculating the self-inductance of a solenoid. So here we used the energy method.